Is it recording?
Yep.
Okay.
Okay, so the goals of dynamic meteorology. This is covering both ATM121a and 121b. The main focus of ATM121a was on so-called diagnosis. That is, looking at the features of the atmosphere in order to understand what exactly is going on. The focus of 121b has been mainly on prognosis. That is, trying to develop equations and an understanding of the atmosphere sufficient that allows us to actually predict the future. This is based on our understanding of the general circulation of the troposphere being the region of the atmosphere where the majority of weather-like phenomenon exist. The upper troposphere tends to be in geostrophic balance due to the fact that there's no inherent bottom friction associated with it. The surface layer tends to be much more influenced by surface friction and tends to have a lot more rotational activity associated with surface lows. In the upper troposphere, you generally have stronger wave-like behavior. Hence, you have synoptic scale waves which appear in the upper troposphere and very few eddy-like features, whereas the eddy-like features are very prominent in the lower troposphere. The general circulation is generally driven by the existence of the Hadley cell, which causes rising motion at the equator, northward propagation along the top of the troposphere, and due to the existence of Coriolis force in the northern hemisphere, you then have a tendency for the flow to turn to the right, and hence you have westerly motion in the northern hemisphere. And hence the existence of a westerly jet at about 30 degrees north and 30 degrees south, known as the subtropical jet, where you have strong westerly winds in that region and strong baroclinicity. Previously we learned by looking at a map of wind speeds in the atmosphere, here for instance showing an emphasis on the polar jet, one can look at wind speeds and be able to diagnose vorticity from these fields. Vorticity comes in two parts, rotational and shear vorticity. Both are important for atmospheric flows. Note that vorticity, although it's describing basically curvature of flow, that is the tendency for objects inserted into the flow to rotate, it does not purely exist along curved lines, along curvature in geopotential. But instead, you can have shearing phenomenon, such as seen here, where you have a change in the direction of the velocity field over a short distance, which leads to the existence of shearing in the flow. In addition, we also have rotational vorticity, which can occur around an isolated low-pressure system, for instance, in which you have rotation about that low as the flow maintains geostrophic balance. So from this plot, then, one can draw on the 500 millibar vorticity, and in particular, you'll observe that vorticity values are largest in the regions where you have that shear and in regions where you have strong rotation. Another region of shear appears up here. Temperature gradients are also closely associated with wind speeds, here showing 500 millibar wind speeds, so in the mid to upper troposphere. These are affected, wind speeds are affected via the thermal wind relationship, which basically says that the vertical shear associated with wind is given by horizontal temperature gradients. That is, in regions where you have strong horizontal temperature gradients in the layer beneath a particular pressure surface, you will have strong wind speeds. Whereas in regions where you have weak temperature gradients, you'll typically have weak wind speeds near the top of the troposphere. So from this, then, if we have a map of the upper level wind speeds, we can then use this in order to determine where the strongest variations in temperature can be found in the layers beneath that. So in particular, where we have the strongest wind speeds, those are the regions with strongest baroclinicity and strongest horizontal temperature gradients. So looking at 850 millibar temperature, you'll notice that the strongest temperature gradients, where it transitions from warmer colors to cooler colors, occurs in this region where we have very strong upper level velocity fields. Whereas in regions where you have very weak temperature gradients, those typically correspond to weak upper level winds. So the first thing that we focused on then was studying the rotational properties of the atmosphere. The atmosphere, to a large degree, is divergence-free. That is, taking the horizontal divergence of the atmosphere leads to a quantity which is approximately 1 order of magnitude smaller than that due to the rotational part of the atmosphere. The reason for this can be seen by simply taking the divergence of the geostrophic wind, which ends up being exactly 0 along pressure surfaces, or small along height surfaces. Consequently, rotation is the dominant mechanism by which dynamics occurs within the atmosphere. And so it is the component that we generally focus on in order to build a prognostic understanding of the atmosphere. So the atmosphere can be broken up into both a rotational component and a divergent component. This can be done for any two-dimensional velocity field, and this is known as the Helmholtz decomposition. Basically, you decompose it into a vector field, which is curl-free, and a vector field, which is divergence-free. The curl-free vector field, that is the divergent component of the flow, is then typically much smaller than the divergence-free component of the vector field. So rotation is particularly important in the atmosphere around low and high pressure systems, and via the geostrophic relationship determines basically the direction of flow around those systems. We've seen that vorticity can be decomposed into two components over the planetary surface. Relative vorticity, which measures vorticity above a certain location, relative to the Earth's surface, and planetary vorticity, which is rotation associated with the fact that the Earth is rotating at a particular rate. Conservation of angular momentum is a concept which occurs within an inertial frame, that is a frame which is not rotating. So when we transform the equations of motion into the rotating frame, we need to take into account that conservation of momentum needs to account for the presence of planetary rotation in the flow. So consequently, what we see is that conservation of angular momentum must be applied to the absolute vorticity of the flow, not the relative vorticity of the flow. Planetary vorticity always points along the axis of rotation associated with the Earth. For vorticity, we are primarily interested in rotation which occurs with an axis perpendicular to the Earth's surface. So although vorticity itself is a 3D vector, the component of vorticity that we're primarily interested in is the vorticity about a vertical axis, that is rotation, which is occurring in the horizontal plane. The component of vorticity that contributes to that then varies depending on where on the Earth's surface you are. If you're at the poles, your vertical axis of rotation is perfectly aligned with the planet's axis of rotation, and hence you'll have maximum contribution from planetary vorticity. At the equator, these two vectors are perfectly perpendicular to one another, and so there will be no contribution from the axis of rotation, so from planetary vorticity to the axis of rotation. The net effect is that the planetary vorticity, which is determined by the Coriolis parameter f, 2 omega sine phi, is 0 at the equator and maximal at the poles. So from vorticity, there were a number of concepts which arose. Given relative velocity field, UVW, with zonal velocity U, meridional velocity V, and vertical velocity W, we can derive a 3D vorticity vector by taking the curl of that vector field. Recall, curl of something gives a vector field back. So this corresponds to the axis of rotation about a zonal vector, so rotation like this. This is rotation about a meridional vector, so rotation like this. And this is rotation about a vertical vector, so rotation like this. So the relative vorticity then is going to be the 3D vorticity vector dotted with the vertical component. That is simply isolating the vertical component of vorticity. And so that's given by dv dx minus du dy. Absolute vorticity is obtained by accounting for rotation of the coordinate system. That is, including planetary vorticity in the computation, and so it is the sum of relative vorticity plus planetary vorticity, or zeta plus f. Here planetary vorticity is k dotted with the curl of the Earth's natural rotation field, solid body rotation, and that's given by 2 omega sine phi. By taking the curl of the momentum equations, we were able to derive the vorticity equation, which gives us a mechanism by which we can compute a time derivative of the absolute vorticity field. The time derivative is then expressed as a material derivative, which includes both local rate of change as well as advection of vorticity. When we took the curl of the momentum equations, we found that 3 terms popped out from this expansion. The divergence term, which is equal to minus absolute vorticity times the divergence of the velocity field. Note this is not the divergence of the velocity field, not the divergence of the vorticity. This is divergence times absolute vorticity, and that basically gave us an influence on angular velocity analogous to that of a spinning skater. That is, if you reduce the radius of somebody spinning, their velocity, angular velocity, will tend to increase. If you expand the radius, then angular velocity will tend to decrease. This is simple conservation of angular momentum. In addition, we also had a tilting and twisting term, which had to do with transitions of vorticity from a horizontal axis into a vertical axis due to tilting of that axis, as well as a solenoidal term. The solenoidal term had to do with misalignment of density and pressure surfaces. And it basically had to do with baroclinicity in the flow. It says that if you have misalignment between the 2 surfaces, then that misalignment will tend to generate vorticity. If you have alignment between the 2 surfaces, you may still generate velocity due to pressure gradient force, but that velocity will have 0 vortical component. It will not be irrotational. Okay? So this came up in when we were looking at frontal activity for quasi-geostrophic flow, because in fronts there are strongly baroclinic features, and hence led to the generation of vorticity in the horizontal plane. So that's not described by this vorticity equation, but an analogous vorticity equation could be derived for horizontal rotation. The net effect was that you had rising motion in front of the front and sinking motion behind. So the vorticity equation had a divergence term, tilting term, and solenoidal term. We did a scale analysis on these terms and found that the tilting term and the solenoidal term were both 1 order of magnitude smaller than the material derivative term and the divergence term. And consequently, in coming up with our vorticity equation to describe large-scale mid-latitudinal weather fields, primarily the divergence term was the only thing that was important. So we neglected the other terms from this equation in order to come up with a simplified vorticity equation. So large terms appear here in the blue box, small terms appear below that line. Via scale analysis, we can say for large-scale mid-latitudinal systems, quantities within this box are the relevant ones for large-scale mid-latitudinal weather systems. From there, we were able to show that that equation, simply using the divergence terms, simplified to simply the horizontal material derivative of this quantity here, known as the barotropic potential vorticity. This describes the vorticity associated with a fluid column, and the fact that this potential vorticity must be conserved following a fluid column. So if your fluid column stretches, then you're going to have a corresponding change in the relative vorticity associated with that fluid column to account for the stretching. And that's due to the non-divergent character of the atmosphere. The fact that if you stretch a fluid column, the volume of the fluid column will tend to be conserved, and so stretching the fluid column meant that the radius would have to shrink. A shrunk radius meant that you have to have faster angular velocity associated with it. So this is again a consequence of conservation of angular momentum. So this was useful in order to understand large-scale wave-like motion, which is the dominant type of dynamics within the mid-latitudinal atmosphere. Here we have large-scale waves, which dominate the background flow for the atmosphere with generally wave number 5 to 6. In the wave-like motion section, we showed that these were actually barotropic Rossby waves. For understanding vorticity, however, we showed that this wave-like motion is created due to conservation of barotropic potential vorticity. And the fact that as you go south of a reference latitude, conservation of potential vorticity said that you need to introduce curvature into the flow in order to compensate for the fact that your planetary vorticity has changed. So south of the reference latitude for a westerly flow, you need to have curvature, which forces the fluid parcel to go north again. And north of the reference latitude, you need to have curvature, which forces the fluid parcel to go to the south. So the net effect is you have an oscillation about a reference latitude due to conservation of potential vortices. These wave-like flows can be triggered by any zonal asymmetry in the flow. One of the most prominent zonal asymmetries that we saw was basically topography. The existence of the Rocky Mountains in western North America leads to the generation of large-scale waves via the large-scale synoptic planetary waves, via the procedure that we discussed here. Namely, when you have a mountain, you have to have that air is lifted as it passes over the mountain. This has a tendency to push up the tropopause, or the surfaces of constant potential temperature above that mountain, and hence leads to stretching of the fluid column as it passes over the mountain. Stretching of the fluid column is then associated with changes in the relative vorticity of that fluid column. The effect is that as the fluid column passes before the mountain, you have stretching, so you need to have the generation of negative relative vorticity in the northern hemisphere. And as it passes over the top of the mountain, you have compression of the fluid column, leading to the generation of positive relative vorticity. The net effect then is as the fluid column approaches the mountain, it's stretched upwards in this location and hence generates negative relative vorticity, which causes it to take on, positive relative vorticity here, which causes it to take on counterclockwise rotation. Counterclockwise rotation in the northern hemisphere being associated with positive relative vorticity. The net effect then is that that leads to the fluid column rotating towards the north. Recall that shear vorticity cannot be created in this situation because we assumed meridional symmetry. That is, we assumed everything, there was no y dependency in the vorticity field, which would be necessary for shear vorticity to be generated. So rotational vorticity is generated leading up to the mountain, and so that leads to a northward tilt in fluid columns as they approach the mountain. As it goes over the mountain, you have compression of the fluid column, and by conservation of potential vorticity, you then need to have that the relative vorticity becomes negative. Negative relative vorticity over the mountain then corresponds to southward velocities. And so you get a dive of the fluid column as it passes over the mountain. As it emerges from behind the mountain, it then finds itself south of its reference latitude. It will then continue to oscillate about the reference latitude beyond the mountain. The reason for this being, as it reaches its reference latitude again, what it finds is that it has a net northward velocity associated with it, and so it'll continue northward from that point and just oscillate about that reference latitude in the wake of the mountain. These oscillations are typically on the scale of 6,000 to 10,000 kilometers. So they're quite long and can basically stretch, one wavelength stretches across all of North America. Warming can also affect potential vorticity and can lead to the generation of potential vorticity and relative vorticity, as we saw for the development of a hurricane. Latent heating in the center of the hurricane led to warming of the internal layers. This pushed up the geopotential surfaces above that layer, led to a slope in the geopotential surfaces above that point, and hence outflows at the top of the troposphere. Since that outflow then led to a reduction in total mass of the fluid column, a surface low was generated, leading to convergence at this point. But the net effect is that as this layer was pushed upwards and stretched due to the existence of latent heating, one had stretching of the fluid column, and hence, by conservation of potential vorticity, relative vorticity had to be generated within the flow. And so the latent heating at the center of the hurricane then was then a driver for it to pick up additional rotation. This additional rotation needed to be drawn from the planetary rotation of the Earth, that is the natural background rotation associated with the Earth's rotation, and hence this mechanism is only possible away from the equator where you actually have a planetary vorticity term. All right, so once we understood vorticity, we then took a look at large-scale mid-latitudinal weather disturbances. Two of these we looked at were synoptic scale waves and the baroclinic instability or extratropical cyclone. The baroclinic instability in particular is associated with frontal activity. That is, regions where you have sharp temperature differences along the surface, transitioning from warm air to cool air in the case of a warm front, or from cold air to warm air for a cold front. For a warm front, these fronts typically take up a wedge-like shape as the warm air rises above the cool air. This leads to a long, drawn-out expanse of clouds that occurs behind the front of various altitudes and character. Precipitation is generally spread out over behind these warm fronts, and precipitation tends to be moderate compared to cold fronts. These tend to travel much more slowly because warm fronts just don't have the inertia necessary in order to push on cool, relatively heavy air. Cold fronts, on the other hand, take on a bulldozer-like shape and hence are able to push through warm air more readily and tend to travel faster than warm fronts. These have a much sharper front associated with them, leading to very rapid uplifting of warm air as the cold fronts push through, and hence heavy precipitation that occurs immediately behind the front. These are associated with large-scale cumulonimbus clouds or deep convection in the mid-latitudes. Further, these tend to travel faster than warm fronts and are vertically steep. In order to understand baroclinic instability, we looked at a model of baroclinic instability known as the Norwegian cyclone model. This model started with an initially stationary front separating warm air to the south from cold air to the north. This temperature gradient could be generated by differences in insolation, for instance. So differences in warming between north and south due to the curvature of the Earth. So in the Norwegian cyclone model, we have this initially stationary front set up, separating warm air from cold air. If some perturbation is introduced in the middle of the troposphere, for instance, this will have a tendency to push up layers above it, leading to divergence at the top of the atmosphere, which then leads to reduction in mass of the column of air, which then leads to convergence of air at the surface and the generation of a surface low. The presence of the surface low then, and the stretching of the fluid column that can occur along the front then leads to the generation of vorticity. Hence we end up with spinning motion, which drives to destabilize the stationary front and turn it into more of a sinusoidal type wave. So a wave forms due to an upper level disturbance embedded in the jet stream. The front then develops a kink. So you have this kink between the presence of a warm front as warm air is advected northwards to the east of the surface low, and cold air is advected southwards west of the surface low. Precipitation begins to develop as warm air is pushed up above cold air in both of these regions. A stronger kink develops at the location of the low. You basically get a discontinuity between the two fronts due to the fact that the warm front is going to be moving slower than the cold front. The cold front moves very rapidly to the south and hence tends to move towards the southeast much more rapidly than the warm front is able to propagate northwards to the east of the low. Both of these systems then continue to become more organized, and you get intensification associated with the low. The wave then becomes a mature low pressure system, and the cold front is then able to overtake the warm front, leading to the generation of an occluded front. Here the occluded front forms as the cold front slams into the warm front, leading to rapid uplifting of warm air as these two fronts come into contact with one another. This leads to partial isolation then of the low, and leads to warm air starting to be cut off from fueling the low. So the occluded front is depicted here. Here we see a cold type occluded front, such as the one that we talked about a moment ago, which includes cold air slamming into cool air, leading to rapid uplifting of warm air as it's pushed up due to buoyancy. The final stage of the Norwegian cyclone model then occurs here, where we have warm air cut off from the center, from the low. Extratropical cyclones are cold core systems. The energy that they have in order to keep going is provided by this warm air that is flowing northwards. Once that warm air is cut off, then the extratropical cyclone no longer has any fuel and it will slowly dissipate over time. So this is different from a tropical cyclone, where the fueling of the tropical cyclone is typically pulled from warm, moist ocean waters, leading to latent heating at the core. We derived a number of equations which were then used to understand these phenomena. One of the more prominent ones being the quasi-geostrophic vorticity equation. The quasi-geostrophic vorticity equation basically explained that relative vorticity, geostrophic relative vorticity, evolved in accordance with a stretching term associated with vertical velocities and advection of absolute vorticity. We expanded out the advection of absolute vorticity into advection of relative vorticity and advection of planetary vorticity. And what we found was that the advection of relative vorticity and advection of planetary vorticity both wanted to move the wave in different directions. Advection of relative vorticity wanted to move the wave to the east. Advection of planetary vorticity wanted to move the wave to the west. So for a example synoptic scale wave, like we've seen depicted here, note that this is a barotropic wave, so stretching is assumed to be not contributing to this wave. This is assumed to exist independent of baroclinicity and stretching that may be associated with a baroclinic instability. We have that the advection of relative vorticity tries to drive the relative vorticity maximum, which is a line here, to the east. Note that these, where it's indicated low and high, these are anomalies relative to the background. And they include basically this whole zonal band right here. So this is not supposed to be indicative of an isolated low pressure, but is instead a low which exists along this whole line. Analogously, this is a high which exists along this whole line. Hence we have clockwise rotation about the high, which is the same independent of which line of constant geopotential you find yourself on. Analogously here, we're assuming that the meridional derivative of the geopotential is constant, independent of meridional position, and so the geostrophic wind at this point is roughly constant along each of these lines. So this is a very idealized example of a synoptic scale wave. So make sure you understand this. This is pretty important. What we determined was, by taking the ratio between the planetary advection and the relative vorticity advection, was that whether the wave travels eastward or westward was determined by the relative ratio of these terms. For waves in which planetary vorticity was dominant, you would get westward propagation of the wave. For waves in which relative vorticity advection was dominant, you would get eastward propagation of the wave. So taking the ratio, one found that the relative strength of these two terms was then determined by beta divided by u bar times k squared plus l squared, here given in terms of wavelengths Lx and Ly. And in particular for short waves, this Lx was small, 1 over Lx is large, then 1 over that is small again, and so planetary vorticity advection is going to be smaller than relative vorticity advection in that case. And so for short waves, relative vorticity advection pushes the synoptic scale disturbance to the east, and for long waves, the tendency is for the waves to propagate to the west because planetary vorticity advection is dominant in that case. Okay? we derived a quasi-geostrophic geopotential tendency equation, which was one of the major goals of the class. That is, 121b is focused on prognostic explanations of the atmosphere. So we want to produce a forecasting equation which allows us to determine how the atmosphere will behave going forward. This is a closed form equation purely in terms of the geopotential and geopotential tendency, which allows us to solve for the time derivative of the geopotential at any given point, given an initial distribution of the geopotential. So this can be then used as a forecasting equation in order to find how the geopotential is evolving with respect to time. And the geopotential tendency equation then, we found basically consists of two terms. Here the diabatic term has been neglected from the equation. The two terms are absolute vorticity advection and differential thickness or temperature advection. So here we call thickness is proportional to temperature. So warmer air tends to have thicker layers, larger distance between geopotential surfaces. So these two terms are then the dominant drivers of the evolution of the geopotential for the mid-latitudes. However, they have very different character associated with them. The first term is associated with barotropic behavior, that is where there's no stretching associated with the fluid column. And this basically is associated with propagation of large-scale mid-latitudinal waves. So this is propagation of synoptic scale disturbances. The second term, which is associated with temperature and thickness advection, this is associated with instability, baroclinic instability in this case. If you have baroclinicity within the flow, that is, if you have changes in how the thickness of the flow with respect to height or with respect to pressure, then advection of that quantity will lead to intensification of a baroclinic instability event. So this is responsible for propagation of a wave. This term is responsible for intensification of a wave. This term tends to be prominent at the along the sloping branch of a wave. Here, it's dominant here by driving down the geopotential as the wave propagates to the east, and here by driving up the geopotential as the wave propagates to the east. The intensification term is prominent at A and B, and that's associated with increasing the magnitude of the wave. So driving the wave to be larger. So remember that. Hint, hint. Mathematically, this term is 0 at the crest and trough of the wave. This term is large at the crest and trough of the wave. So using this information, we were able to build our quasi-geostrophic baroclinic disturbance for a westward tilting system, that is one where the low pressure at upper levels is to the west of the low pressure at lower levels. The system tends to develop and tends to look like this. You have a surface pressure which is located along the upward branch of the wave. Note this wave is located at approximately 500 millibars, or 500 hectopascal. The low pressure associated with the wave corresponds to counterclockwise rotation within the wave, and the high pressure corresponds to clockwise rotation in the wave. The low pressure at the surface occurs due to the low level of disturbance that occurred within the baroclinic instability, and the presence of this leads to stretching of the fluid column, and hence why vorticity develops at 500 hectopascal. The development of the vorticity then leads to the development of this wave-like shape associated with the baroclinic disturbance. Let me go back here briefly. I want to mention one more thing. So this is proportional to differential temperature advection, and hence is closely associated with frontal activity. The reason being that temperature gradients tend to be strongest near the surface for fronts. So for warm fronts and cold fronts, temperature gradients at the frontal location will be strongest at the surface. Consequently, near the crest of the wave, you will have a reduction in warm air advection as you go up, and at the trough of the wave, you have a reduction in cold air advection. So these two will have opposite signs to one another, and hence the reason why at the crest of the wave, you will have positive geopotential tendency, and at the trough of the wave, you'll have negative geopotential tendency. Hence the intensification. So for the baroclinic disturbance, at the surface, we have fronts. Frontal activity leads to warm air advection to the east of the low and cold air advection to the west of the low. This is mirrored but smoother at higher levels. At 500 hectopascal, we have a much weaker wave-like character. Cold air advection occurs towards the trough of the wave, and warm air advection occurs towards the crest of the wave. Vorticity advection is most prominent above the surface level low and surface level high, with positive absolute vorticity advection occurring above the surface level low and negative absolute vorticity advection occurring above the surface level high. That leads to propagation of the wave and the tendency for eastward propagation associated with short wavelength baroclinic systems. Vertical velocity, as expected, is positive above the surface level low, and that's due to the fact that we have convergence at the surface associated with the low pressure. Convergence at the surface then drives vertical velocities associated with the flow. High pressures at the surface is associated with subsidence of the flow, and hence why we have negative vertical velocities at this point. This observation can be observed mathematically by looking at the quasi-geostrophic omega equation, and in particular observing that that vertical velocity is determined by advection of absolute vorticity by the thermal wind. Thermal wind here tends to be towards the east, and hence the value of omega will be determined by the sign of the absolute vorticity gradient within each of those regions. So for short waves, we have that UT cross times the zonal derivative of the relative vorticity is positive here, and advection of relative vorticity by the thermal wind is negative here. This corresponds to vertical velocities above the surface low, positive vertical velocities above the surface low, and negative vertical velocities above the surface high. Vertical velocity tends to be roughly 0 at the ridge and trough. Geopotential tendency. Intensification of the baroclinic instability leads to positive geopotential tendency at the ridge, negative geopotential tendency at the trough, and propagation of the wave leads to negative geopotential tendency here and positive geopotential tendency here. So short waves move to the right, long waves move to the left. Okay, then in chapter 6, we looked at wave-like behavior in the atmosphere. Waves are very important for atmospheric dynamics because they transport energy and have a tendency to mix the air when these waves break due to nonlinear effects. We studied Rossby waves, internal gravity waves, inertial waves, and Kelvin waves. In addition, you can check out the bonus lecture in order to learn about other tropical waves, which include mixed Rossby gravity waves, equatorial Rossby waves, and equatorial inertial gravity waves. Sound waves are not particularly important for meteorology, so we didn't really study those. Understand this. This is the mathematical description of how waves basically appear within the atmosphere. You have wave number. You have a wavelength, which is associated with the distance between troughs. Note that the wavelength between troughs is always shorter than the wavelength between troughs in each coordinate direction. And we have wave numbers given by 2 pi over the x wavelength and the y wavelength for k and l, and these can be combined to produce a wave number vector magnitude given by square root k squared plus l squared. So the first type of wave we looked at was barotropic Rossby waves, shown here. We derived a dispersion relation associated with them. Try to make sure you understand how exactly we got to the dispersion relation associated with these waves. And using our knowledge of phase speed and group speed, phase speed being the speed at which individual crests propagate, and group speed being the speed at which the energy associated with the wave propagates, we obtained this information about the propagation of Rossby waves. And in particular, we learned that these waves always propagate westward relative to the mean flow. Whereas energy propagation can be either westward or eastward depending on the signs of K and L. These waves are also dispersive. Dispersive meaning that the phase speed is a function of the wave number. We looked at internal gravity waves, which are oscillations which occur within the fluid due to the fact that we have constant stratification. Constant stratification with height in the atmosphere. That is, density is a function of height and is not purely a constant value with a discontinuity. So these waves can propagate due to internal oscillations and are associated with buoyancy within the atmosphere. That is, they only occur when you have a stable atmosphere and a positive Brunt-Väisälä frequency. And these are due to oscillations of individual fluid parcels about a reference height due to buoyancy force as the restoring force. There we go. Need more coffee. Topographic gravity waves are an example of internal gravity waves. These are driven by underlying topography. Internal gravity waves have interesting character associated with them. Phase lines, for instance, for k greater than 0 and m less than 0 are pointed from bottom left to top right. Phase speed is towards the surface. So you have waves which propagate over time, will propagate in this direction. But the actual velocities within the wave are perpendicular to the phase speed. So the velocities are actually aligned to the top and to the right. This is also the direction in which the group speed is aligned. So propagation of energy actually occurs in that direction, as seen here. We observe that pressure is aligned with maxima in the velocity field, but temperature perturbations are a quarter of a wavelength offset. Topographic waves were a particularly prominent example of internal gravity waves, and these are due to forcing from the surface due to underlying topography. These are stationary waves, which means they have no variation in time and simply sit within the atmosphere due to the presence of a mean background flow interacting with topography. They have the ability then to propagate energy upwards in the atmosphere away from topography. For small k, which is associated with a wide, broad mountain, we get so-called vertically propagating waves. These occur because the solution of the dispersion relationship yields values of m which are real. That is, have purely wave-like character associated with them. These type of waves tend to tilt westwards with a wave number vector that points up to the right and a group velocity which points upwards away from the surface. For large k, we have a narrow mountain, so very rapid variation in topography over short distances. This leads to m, which is purely imaginary, and hence waves which decay with height, but are locked relative to topography. That is, they have no vertical propagation associated with them, but instead have the same profile as the underlying topography, but decay in magnitude as you go up in the atmosphere. And this occurs because m is purely imaginary, and hence the waves associated with this system experience an e to the minus mi z term. For mi positive, this then leads to exponential decay with height. These type of waves have no tilt and no vertical momentum transport associated with them. We talked about tropical dynamics briefly and discussed the differences between the tropics and the mid-latitudes. Particularly in the tropics, you have no Coriolis force. and you have very weak horizontal temperature gradients. Weak horizontal temperature gradients due to latent heating in the atmosphere being a dominant mechanism by which, being kind of a stabilizing force for spreading out the temperature gradient within that region. Convergence at the surface near the equator, driven by the returning branch of the Hadley cell, leads to deep convection along the intertropical convergence zone, and hence the appearance of small, discrete, deep convective events, which are then associated with splotchy cloud formations. This is different from the mid-latitudes, where we see more filamentary type clouds. We also observed in the equatorial regions, we have the Walker circulation, which is a zonal circulation driven by land-sea temperature differences. When looking at waves in the equatorial regions, we discussed two types of waves: coastal Kelvin waves, which actually occur regardless of where you are on Earth, whether in the mid-latitudes. They're driven by an F plane, so they're dominant in the mid-latitudes, and equatorial Kelvin waves, which are driven by beta plane effects and hence occur along the equator itself. Kelvin waves can only propagate in one direction. They are trapped waves, so they're associated with a particular boundary, either being a coastline or the equator itself, with exponential decay in the magnitude of the wave as you get away from that boundary. Both coastal Kelvin waves and equatorial Kelvin waves satisfy this, this character of trapped waves. Equatorial Kelvin waves are obtained by solving the shallow water equations for this magnitude perturbation U hat. They have a wave speed which is non-dispersive, simply given by the inertia gravity wave speed, square root of GH. And this term always has to be positive in order to preserve the fact that these waves decay away from the equator. So these waves always propagate eastward. They propagate along the equator. Coastal Kelvin waves propagate northwards along the eastern side of a fluid, so along the west coast of North America. Along the California coast, these waves propagate northward, and along the west coast, they propagate southward. Coastal Kelvin waves then are an example of a phenomenon which drive higher ocean tides near the French coast than along the English coast, because of the fact that these waves are propagating along the eastern coastline in that case. All right, that's everything. Questions?
Wow, dude, 1150.
Yeah.
Here are the definitions you need to know.
Is that really 73 slides?
Well, including this bit.
Oh, okay.
So it's probably like 60 slides or something like that. Definitions for chapter 4 you need to know. Concepts for chapter 4 you need to know. More concepts. Questions you need to know. Questions, concepts for chapter 5, definitions for chapter 5, questions. Chapter 6, definitions, concepts, and questions. That's it. So, great having you guys. Thank you very much. I hope you learned something. And read over the material and send me an email, give me a call, or come to office hours next Monday. Okay?